in series and driven from the single phase source. Not only input displacement factor, but if you find out its harmonic spectrum, that harmonic spectrum is also improved. This is about half controlled converters. The next in this category is simultaneous control of fully controlled converters. What is the simultaneous control? Again, you have multiple converters in series. Let us say there are two converters. And these converters are fully controlled converters. Say this is converter 1 and say this is converter 2. Now if you want output voltage positive, what is done? Converter 1 is operated at firing angle 0 and converter 2 is operated at firing angle alpha 2. The resultant is like this. Converter 1 operated at alpha 1 0. This is the output voltage. And converter 2 operated at a firing angle alpha 2. This is the output voltage. It's a fully controlled converter. This is the firing angle alpha 2. Both these voltages are same. These are the output voltages of 1 and 2. If you simply add them, this positive portion will be cancelled by this negative portion and the resultant voltage will be, this positive portion will be cancelled by this negative portion. You can see this output voltage is similar to half controlled converter, and therefore not only the voltage, even if you see the current, this is the input current due to converter 1 and this is the input current due to converter 2, and if you add them, plus minus get cancelled, double the current 0, double the current 0. So the voltage and the current waveform are identical to half controlled converter, and therefore this particular curve is applicable. Just like a half controlled converter, or you can say controlled freewheeling. If you want output voltage negative, that is between 0 and -1, here what we did, here we kept alpha 1 0 and alpha 2 is controlled. By increasing alpha 2 towards pi, when it becomes pi, the positive output voltage of this gets cancelled with the negative output voltage and the output voltage becomes 0. Now keeping this alpha 2 pi, alpha 1 is now increased from 0 value. So what happens to the output voltages of the two converters? Output voltage of converter 1 will be like this. It is operated at a firing angle alpha 1. And converter 2 output voltage will be completely negative because firing angle alpha 2 is pi. Now if you add these two voltages to find out the resultant one, minus minus it becomes double minus. Plus minus it gets cancelled. Then minus minus it becomes and then 0. Just see, this firing, this output voltage is similar to controlled freewheeling inversion mode, and if it is a controlled freewheeling inversion mode, then this particular curve is applicable, locus is applicable. So simultaneous control of fully controlled converters, both the converters are in operation. If to get output voltage positive, one firing angle is kept 0, another is increased. By increasing it to pi, output voltage will become 0 from maximum. Keeping it pi, now alpha 1 is increased, you will get the output voltage negative. And as far as current waveform is concerned, current waveform will be like this. This is due to converter 1, and here firing angle is 180 degree. It is just opposite. If you add these two, you have double the current, minus plus it gets cancelled, plus plus this is simultaneous control of fully controlled converter. You can also have sequence control of fully controlled converters with controlled freewheeling. circuit is same. Controlled freewheeling operation gives you improvement in power factor. That's what we have seen. Now, if you want output voltage between 0 and 0.5, if you want output voltage between 0 and 0.5, what is done? Converter 1 is operated in a controlled freewheeling mode, and converter 2 is bypassed. Bypassing a converter means the two devices of the same leg are triggered so that it will not contribute to any voltage, it simply provides a path for the current. Only this converter is in operation and it is operated in a controlled freewheeling mode, so the output voltage of the converter will be like this. And this curve is similar to by reducing the firing angle you can have the maximum 50% output voltage. If you want output voltage between 0.5 and 1, then converter 1 is operated at alpha 0 and converter 2 is in controlled freewheeling mode. So what will be the output voltage? Converter 1 output voltage will be like this, and the converter 2 output voltage will be a controlled freewheeling. And the resultant voltage this will give you voltage versus the reactive power curve like this. If you want output voltage negative, if you want output voltage negative, just like previous case, one of the converter is in controlled freewheeling mode and one of the converter is bypassed. Output voltage you want negative. We know how to trigger the thyristors of this so that the output voltage waveform is like this, negative voltage. And in this case, negative voltage and the reactive power curve will be like this. If you want output voltage between -1 and -0.5, then one of the converter operates at alpha pi and another converter operates at an angle alpha, a controlled freewheeling mode. So what is the result? One of the converter provides the output voltage negative, firing angle is pi. Another converter provides the output voltage like this, and the resultant output voltage will be And if you find out its reactive power versus voltage curve, so fully controlled converter input displacement factor is quite poor. It can be improved if we use half controlled converter, but then it is possible to have only positive voltage. If we go for the controlled freewheeling mode, we can have both positive and the negative voltage with the performance similar to half controlled converters. We can go for the sequence control of converters to further reduce the power, reactive power requirement, and that improves the input displacement factor. If we simply go for the half control converters or the simultaneous control of converters, we can have only positive voltage. But if we go for sequence control of fully controlled converters with controlled freewheeling, we can have both positive and the negative voltage. Multiple converters in this way can be used to improve the input displacement factor. This is the third technique, and it is applicable basically to single phase converters. There is one technique which is applicable only for three phase converter, and that is also based on line commutated thyristors. The technique is called, the converter is little bit modified, it is called four-leg converter. Normally we have three-phase, three-leg converters, but here you have one more leg. And this is the load. The three legs are connected to RYB phases like previous or the conventional converters. And this fourth leg, it is connected to neutral. And the devices are numbered like this: 1, 3, 5, 4, 6, 2, no change. This is numbered 7 and this is numbered 8. 7 and 8 are the thyristors which basically provide freewheeling operation. The analysis of this converter can be done just by dividing it into two parts, as we did in the beginning for a three-phase converter. So you have thyristor 1, 3 and 5, and this is 7. You can see it is similar to your freewheeling diode in case of three-phase half-wave converter. and the other one you can have this is R, Y, B. So you have R phase, that is 4, 6 and 2, and this is 8. This is neutral. Now it is easy to analyze these two. Before we see the operation of this, one point we'll have to re-examine, and that is the firing angle. Just recall, we have seen that in case of a three-phase bridge converter, from which particular point the firing angle is measured. If you talk in terms of the phase voltage, whenever R phase becomes maximum positive, that is alpha is equal to 0 for TH1. Similarly, when Y phase become maximum positive, that is alpha is equal to 0 for TH3. And when B phase becomes maximum positive, that is alpha is equal to 0 for TH5. Because the firing angle is measured from the instant when the device becomes just forward bias. Whenever any of the device conducts, a voltage appears across the load. If that voltage is just becoming negative, it means this thyristor 7 is getting forward bias. And therefore, the firing angle for thyristor 7 is measured when this particular output voltage, if I say VO1, that becomes just negative. If VO1 becomes just negative, that is the firing angle 0 for thyristor 7, and that firing angle we say is delta. Similarly, as far as these three thyristors are concerned, R becoming maximum negative, that is alpha is equal to 0 for TH4. Y becoming maximum negative, that is alpha is equal to 0 for TH6. And B becoming maximum negative, that is alpha is equal to 0 for TH2. And when any of the thyristor conducts, voltage appears across this. If this voltage, if I say VO2, it becomes just positive, then TH8 becomes forward bias. So if VO2 becomes just positive, that is delta equals to 0 for TH8. Now with this, we can see what will be the output voltage of this particular converter. Just use the templates that I have. This is the case when the firing angle alpha is 30 degree. We know how to find out the output voltage of this converter and this converter. If alpha is 30 degree, you can say this is the output voltage and it is all throughout positive. It is never becoming negative. Alpha is measured from the intersection point of the phase voltage. This is alpha is equal to 0 for TH1 and 30 degree. So this is the output voltage. And assuming the load current to be continuous or constant, we have the output voltage of converter 1 upper half like this. And similarly, when R phase becomes maximum negative, that is alpha is equal to 0 for TH4, triggered at a firing angle 30 degree. So this blue color line indicates the output voltage of converter 2, that is VO2. Just see here what is VO1 and what is VO2. And you can find out the resultant voltage, that is this particular vertical line. So it is R phase minus Y phase, so it is the line to line voltage RY. You can see on this particular one, both the line voltage and the phase voltages are shown, and there is a reason why we have shown it like this. Now delta equals to 0. So this is the instant when the voltage tries to go negative, but before that 3 is triggered, so it becomes positive. It means thyristor 7 is just becoming forward bias, and that's all. Only for short duration, only at a particular point it is becoming forward bias. It cannot be triggered there. So 7 and 8 they will not conduct at all. For 7 this is delta equals to 0. For 8 this is delta equals to 0 when it tries to become positive. So 7 and 8 are not triggered, and if 7 and 8 are not triggered, it is as good as a 3-phase fully controlled bridge converter. Since the firing angle is 30 degree, so the output voltage is like this. Input current will be of this nature, and fundamental current is this one, green color. Phi 1 angle is same as 30 degree, so input displacement factor is cos of alpha. So there is no change in the operation in this particular case. That thing we can also represent. I'll just remove this, not required, no, this one. If you recall the output voltage as a function of alpha, it is basically like this. Alpha 0, this is pi by 2, and this is pi. This is 1.0 and this is minus 8. Now when alpha, this is conventional one. If you have this 4-leg converter up to 30 degree, you can say there is no change. So the output voltage as a function of alpha is same. Consider the second case. Firing angle is 60 degree, but delta is 0. 60 degree means it is triggered here. So TH1 is triggered, it follows R phase and tries to go in the negative direction. But when it goes in the negative, thyristor 7 will become forward bias. And the firing angle of thyristor 7 is measured from here. It is triggered at delta equals to 0, so the output voltage will become 0. Then 3 is triggered, then again 7 is triggered, then 5, then again 7. You are all the time positive output voltage, that is of converter 1, upper half. Similarly, 2 is triggered here, it tries, it goes like this, and from here it will try to become positive, but then thyristor 8 becomes forward bias. And when 8 becomes forward bias, you can trigger at delta equals to 0, output becomes 0. And then 4 is triggered. Again it tries to become positive, but you trigger 8, so it becomes 0, then 6, so you have the voltage. Now, if you find out what is the resultant line to line resultant output voltage, see, from this point to this point, this is your B phase and this is your Y phase, so it is the line to line voltage By. But from this point to this point, this is 0, this is Y, so it is 0 minus Y, it becomes minus Y. Minus Y means Y is like this, minus Y like this. Then you have R phase and Y phase, so the difference is Ry, like conventional. But from this point onwards, this is R, this is 0, so it becomes only the R phase. That's why the reason why both line and the phase voltages are drawn here, because output voltage may be the line voltage, line to line voltage, or it is the phase voltage, and in this way the operation takes place. As far as current is concerned, see, when TH1 conducts, this is the period during which current flows through R phase, and here it is a freewheeling. And when thyristor 4 conducts, negative current flows like this. And fundamental current you can draw like this. How much is this angle? This is 60 degree plus 30, so 90 degree. Half of that 45 degree. It means input displacement factor has become cos of 45. For the same output voltage, if you see the fully controlled converter, the firing angle would have been higher and the input displacement factor will be poorer. Because of this, you can see the output voltage has increased, and therefore instead of following this curve, now it will follow this particular curve. It will become more. If you see next condition, alpha is equal to, let us say, 120 degree. Again, during this period, output voltage appears, then freewheeling, 7 conducts, then output voltage, then freewheeling. Similarly, in the lower half, output voltage, freewheeling, output voltage, freewheeling. As far as 1, 2, 3, 4, 5 and 6